And he's going to talk about spectral density of individual trajectories of active particles.
Okay, thank you, Sally. And yeah, first of all, I want to thanks all the organizers for giving me the opportunity to present what kept me busy during the lockdown, actually. And well, it's always a nice opportunity to be here. I feel like back home in a sense. And yeah, and maybe I have to apologize because I won't talk about memory kernels and explicitly non-Markovian systems, and with the exception of the last slide, just it will allow me to fit into the scope of the event. Yeah. So what I'm going to present is a joint work done in collaboration with Gleb Oshanin, Alexandre Solon from Sorbonne, and this is based on this paper here, and which is actually a continuation of our program of extending the notion of power spectral density to finite time trajectories, single trajectories. So essentially, we are building up a sort of catalog. So we started with the Brownian motion, then the fractional Brownian motion, and here we are considering the active Brownian particle. Okay, so let me briefly remind you what the power spectral density is. As all of you know, I don't have to explain maybe, so the PSD briefly will, this is what I will tell, will be the power spectral density. So it embodies a wealth of property of the stochastic process under consideration. This is, in any textbook, let's take a continuous process. It is defined like that. So you take your trajectory x, we have this finite Fourier transform, take the modulus square, take the observation time t going to infinity. And as you know, and as you see, this definition implicitly assumes two things. First of all, the possibility to take an ensemble averages, which is, in many situations, it's not feasible, such as in vivo systems or in instances where you really cannot reproduce your trajectory. And so sampling is a problem. And there is also another problem that the observation time is finite, of course, in simulation and in many experiments. And for some situation, it is also tricky from the mathematical viewpoint. So the aim is to extend the definition in order to relax, essentially, these two features. So we define the single trajectory spectral density. Essentially, we are not taking the average in the previous definition, and we are keeping the observation time finite. So this is the single trajectory spectral density, this object here. So as you see, S is obviously a random process itself. So, and if you take the average of this, you have a finite time power spectral density. And in order to compute that and moments of that, you need the autocorrelation function of the trajectory of the itself. And the textbook definition is retrieved when you take the infinite time limit consistently. So, and for me, for us, the motivations that prompted the study of the active Brownian particle in this setup is that the power spectral density, single trajectory defined, has not been yet investigated. So this was for us a good reason to do it. It brings also some mathematical challenges. So another interesting reason to do it. And maybe more physically, the scope eventually is to distinguish between active and passive Brownian motion simply by looking at spectral properties. Yeah. So the model, I can come now pragmatically to the model. I am simply referring to the same model already studied by Satya and co-workers some years ago here in this paper. So this is our model for the active Brownian particle. It can be, let's say, a Janus colloid, which is trapped at an interface. So it moves into D. And we can also assume that the rotation occurs in the same plane where the motion takes place. So these are the equations of motion. So x dot is equal to the cos of theta, and analogously for y dot. Theta of t is the polar angle, which is a random walk. So zero average, and this is the correlation function for the angular coordinate. And as you see, the velocity is constant, so all the motion is completely codified by this equation and by the randomness inside the angular variable. And d of r is the diffusion for rotational diffusion, this coefficient of rotational diffusion, and tau r will be the inverse of dr. Yes. Taking all these initial conditions to 0 doesn't play any particular role, so it's just a mathematical simplification. So starting with that equation of motion, it is very easy to compute something like the velocity correlations. Also, these are 2-point velocity correlations, but you can go also to 4 points and stuff like that. But the message is the following. So provided you take times t1 and t2, which are much larger than tau r in separation, and then you get a complete decoupling. So essentially, you lose correlation in an exponential fashion. Notice that the Langevin equation, which describe the motion, as you see here, they contain the noise inside the trigonometric functions. So it means that the noise enters into a nonlinear fashion in the game. And if you wish, this is actually the correlation function of the nonlinear noise, if you want. Another feature of the model is that the velocity is constant in absolute values, in magnitude. So there are some constraints. So x dot square plus y dot square, even without the average, has to be constant. So it means that the two components of the motion will be strongly correlated. And as it will appear in a moment, so the active Brownian particle will actually resemble the Brownian motion, but only in this regime where you have this decoupling, provided you define an effective diffusion, of course. Okay, coming to the power spectral density, as I told you before, it is essential to know this correlation function of xx and yy. And this can be computed by standard techniques. For instance, you can use the method of characteristic functions, and you get results like that. Then you have to plug all this junk into the machinery and do the calculation. So as you understand, it will be quite cumbersome. And but before commenting on that, I can comment on what the mean square displacements are. And as you see, you simply have to set t1 equal to t2 in the previous expressions. And so there is an interesting fact. So for short times compared to the rotational time, the mean square displacement along x and along y, they are strongly anisotropic, as you maybe expect. So here you have a directed motion along x and a cubic behavior along y. But this is actually due to the fact that the system remembers the initial condition just for short times. But as soon as you move away from this short time regime and you go into the large time regime, both of them become asymptotically equivalent to the standard Brownian motion, provided you introduce this effective diffusion coefficient. So they become linear. And okay, now I can come to the single trajectory spectral density in the infinite time limit. This is the only compact result I will show you in this talk, because otherwise they will become too cumbersome. And so in this regime, so mu x and mu y, they don't make any difference, so they are the same. The result is a 1 over f squared behavior, which is actually similar, analogous to the one you have for the Brownian motion, standard Brownian motion. On top of that, we have also which appears in a multiplicative fashion, a Lorentzian factor. And this Lorentzian factor is actually quite analogous to the one already obtained by Satyan and Gleboshan in the case of stochastic reset, although they have the power with the Hurst exponent, which we don't appear here, obviously. And yes, and if you take, for instance, the limit of f going to 0, so 0 frequency, you are capturing the late time behavior. This goes away. They two sum up to the same quantity, and you get the standard Brownian motion result. So in a sense, as I told you, so it becomes a Brownian motion at late times. And of course, for large frequencies, you have still this behavior, again, similar to the Brownian motion, but with a different prefactor. And okay, now I can show you what's happening if you keep a finite observation time. So this is, in square brackets, you see the results for the pure Brownian motion. Okay. Yes, which, by the way, it's formally identical to the structure factor of an easing interface trapped onto a strip, but this is a side remark. And so the power spectral density by dimensional analysis can be cast into this way, and this is the rescale frequency, and this is the rescale PSD. So here you get the standard log-log plot, which you always do when you do spectral analysis. So here you see the 1 over f squared behavior, and here, as soon as you change the amount of the observation time, you have different curves. And it is important to notice that the value which you get when the frequency is 0 has itself a particular meaning. If you wait 3 slides, you will see what it is. Well, there is a spoiler here, okay. Okay. And yes, what we did in those two papers which I mentioned at the introduction is that we focused on the coefficient of variation, which is the variance divided by the mean of the fluctuating single trajectory spectral density. And this is what we did in those two papers which I mentioned at the beginning, for the Brownian motion and for the fractional Brownian motion. And then we compared those analytical curves with the experimental findings. So here we don't have experimental findings, but the idea is the same. So first of all, to get the plot. And this is the first, and here we have a first remarkable difference compared to the former cases, let's say. So if we take an infinite amount of times, so the coefficient of variation is not a pure number, say a universal number, let's say, as it was in the previous setup. For instance, in the case of the Brownian motion, taking the infinite time limit gives you square root of 5 divided by 2 and full stop. Here instead, we don't have anything like that. So the infinite time limit of the coefficient of variation still depends on the activity, let's say, on the dr or tau r, no matter how we want to call it. So, and this is the dependence on the parameter of the model. And however, there is an upper bound, which is the same upper bound which we observe for the super diffusive fractional Brownian motion, which is square root of 2. So there is a strict bound here. And this is what's happening. So ideally, the ideal situation would be to supplement this curve or to complement with some experimental data. So, but we don't have them. Then the functional S of x has to satisfy some constraints. So if you take the full integration over the frequency domain, we need to recover the mean square displacements, as was observed by Barkai and co-workers in this paper, up to a factor pi. And this is what actually it's happening. So, so this was somehow a consistency check. As I was telling you before, if you take the zero frequency limit, you get access to the square area average, which is attained by the random process. This is mu of x, and this is the average area square. And of course, you can do the same for mu y, but you get different prefactors. And we can study this quantity. For large times, we get the t-cube dependence, which is the same, identically the same for the Brownian motion, with that the effective diffusion coefficient. And for small time, we get a, let's say, transient ballistic regime, so a t to the 4th. And this is the other property of the power spectral density at zero frequency. And then coming again now to the finite observation time, what I'm plotting here is the coefficient of variation. And here I am plotting the Pearson correlation coefficient between the component S of x and S of y. Why? So the reason is that S of x and S of y are entangled or correlated simply because they are emerging from the same noise coupled to sine and cosine. So the resulting correlation between S of x and S of y is something quite non-trivial. And indeed, so S of x and S of y are positively correlated, as you see here. And of course, if you take the limit of infinite observation time, you project onto a perfect correlation. And then if you take instead the limit of infinite time of rotational diffusion, so say differently, zero diffusion, coefficient of rotational diffusion, in this case the trajectories no longer fluctuate, so they are frozen, and the Pearson goes to zero, which is quite hard to see maybe in this plot, but this is what is happening. And in this plot on the left-hand side, you see the comparison between the passive case, which is the magenta curve, this curve here, and in the other curves, you see the active case for different observation time. So this was the plot which we compared with experiments in previous papers. So ideally, one would do the same here with this type of plots, and this one also. And yes, as I tacitly assume at the beginning, I simply consider the rotation, the diffusion of the angular degree of freedom as a predominant role in the game, which means that I am simply neglecting the translation. But in principle, you can have also a translational effect into your Langevin description. So, and this is what we are adding here. So we see the effect of a translation on top of the rotation. So by assuming that this is uncoupled to the angular part, we can work out what the mean square displacements are and also repeat the same game. So for instance, just to understand, Alessio, what do you have in mind now? Now I have in mind the same problem as in the previous at the beginning, let's say. So the rotor, but then it jumps. Yes, now instead of having only the rotation here, theta, I have also a thermal. Yeah, so standard. So actually, this is a super simplified model. Yeah. Sorry, I didn't see the. No. Okay. Where are we now? Here. Yeah. And D is the coefficient of translation coming from the, let's say, from the solvent, if you want. And okay, we can repeat all the game, and this is the power spectral density. So it simply gets an additional effect stemming from the solvent in this fashion, which is not surprising. But what we want to do now is to rebuild the coefficient of variation plot. And if you do some dimensional analysis, you see that everything has to depend, since the coefficient of variation is a pure number, on ft, on this ratio of times, and on eventually on the Pecquelet number. And so I construct this parameter alpha, such that alpha equal to 0 corresponds to the Brownian motion, so the pure passive case, no self-propulsion, and alpha going to infinity is the pure active model of the initial slide, let's say. So, and this is the chart for the coefficient of variation as a function of the scale frequency, depending on this activity parameter alpha. So as you see, black is the passive case, which is this curve here. So we observe there is a really non-trivial, non-monotonous dependence on the gamma for a certain frequency on the degree of activity. Because starting from the passive case, we can start to build up activity. We go to the blue curve, then we go to the green, then to the orange, and then to the red. And then we finally, when we reach infinity, do the purely active case. So as you see, there is a really non-monotonic behavior, which is not so easy to understand. But this is something one has to compare with any experimental recording, in fact. And in fact, one can build up a sort of expansion around the purely active case, in terms of 1 over alpha, which is supposed to be small. And concluding, this is something which maybe fits better into the non-Markovian aspects of the event. This is a calculation I was doing some time ago when I was, sorry for this type, when I was in Paris. So here we started to consider the trapping effect on the fractional Brownian motion, which is canonically interesting as a non-Markovian system. And here we wanted to extend the notion of power spectral density, including the effect of confinement and non-Markovianity. And to make this long story short, by introducing in this Langevin description a fractional Gaussian noise for xi, So we derive this expression for the infinite time limit of the power spectral density, which we find quite surprising because of this f to the alpha minus 1 times f squared behavior, which we don't find in the literature. So we regard this as quite nice. But this is actually a work in progress, so I should not comment anymore on that. And I can come now to the summary. So I hope I convinced you that this program of extending the notion of power spectral density to instances of single trajectories and finite time can be done, and it has been done also for the active Brownian particle. I show you some limiting behavior for infinite time and small frequency. And the whole idea of this program is to identify certain features of active or passive motion simply by looking at spectral fingerprints, which are the coefficient of variation, and in this realm also the Pearson correlation coefficient between S of x and S of y. And as you imagine, there are many, many interesting perspectives. And with this, I thank you for your attention.
Okay, thank you. Are there any questions from the students? No? Yeah, okay, great. Yes? Yeah, please.
Can you comment a bit? No, you have to use the microphone, otherwise those online do not hear.
I see. Maybe I missed something, but in the last example where you drag the particle, is there any specific reason for the special kind of noise? You want this, or is it, or it can be motivated in some way?
No, actually, this was a sort of. I wanted to tell you something more about that, but since I don't have time. So the idea here is to consider, again, the power spectral density in presence of confinement. And what we did here is to consider two different situations in which we have memory effects. So in one situation, we have the standard Langevin equation as this one here, but with psi, a fractional Gaussian noise. And when you say that psi is a fractional Gaussian noise, when you take the infinite observation time limit, this is the result you get. So this is one way to introduce memory effects. And of course, if you take white noise, you get the standard result, which is in a textbook, which is this one here. And so this is one, let's say, deformation of the model. The other deformation, it's much more complicated, and it passes through the Langevin equation with a memory kernel power law. And this is much more complicated from the analytical viewpoint. And on top of those results for infinite time, we also work out the finite time corrections, which are very, very nasty. So the idea was simply to get some result for the PSD with memory effects and confinement. But yeah, what I want to emphasize is this exponent, which we find surprising. So.
Okay, so there is one question from the chat. Sorry, I think I missed, but for the cross correlations, you would need CXY kind of correlations, right?
Yeah, when we compute this object, well, it's really a pain. Okay. This is really painful.
I mean, you were in lockdown, so.
Yeah. Yes, but I appreciate the question. So, when I had to compute Sx square, for instance, Sx square, I had to compute the 4-time correlation function of the position with all the kernels and with all the integrals, doing all the combinatorics and taking into account that the noise comes from the trigonometric function. It's not nice. Then you do the same for y. This is okay. And then you do the same for Sx, Sy. And this brings to the xt1, xt2, yt3, yt4 correlation function of the position. Right. So correlation functions of the velocity, piece of cake. Correlation function of the position it's a pain.
Harder, yes. So there is an addendum to this question. What would be the effect of additional time scales like a trap? But I think you have already said it.
Yeah, so that's the super question. So it's the monster. That's why it comes at the end. Ideally, one would like to combine activity, trapping, and everything else, but I don't have the answer.
You have to wait the next lockdown.
No.
Okay, I'll just, yes, please.
So can you go back to can you go back to this Pearson coefficient, so the monster? Yeah.
Yeah.
So can you give any intuition what this means? Is this some sort of temporal ordering that X feeds Y or precedes Y, or how should one understand that? I mean, what
No.
you know?
No, the idea is much more simple. So I know that the components S, X and Y are correlated of the,
No,
and
that
that's
is-
fine.
yeah.
And so I simply want to see how this correlation reflects into the PSD. Okay.
But you didn't go further, so you don't know whether this is because you have a cosine of the same noise, right? So
Yeah. Sine and cosine of the same,
yeah,
noise,
so
of the very same noise.
it could be that just you have this retarded advanced kind of thing of the noise. So
Yeah.
I don't know. I have
but-
no clue. I have no intuition about
But so
this.
I simply took it from the mathematical viewpoint. I have
Okay,
I
okay,
have no
fair
particular
enough.
understanding of.
Fair enough.
of
I mean, in some sense, it's a 4-point correlation function.
Yeah.
it's a 4-point correlation
Okay.
function. Fair enough. So
Yeah.
that's the ontology of this object.
Okay. Thanks.
Okay, so if there are no other questions, so thank you, Alessio, again.
Thank you very much.
And